Welcome to the Blue Waters webinar. I'm Scott Lathrop with the Blue Waters Project at the National Center for Supercomputing Applications at the University of Illinois. It's a pleasure to welcome you to today's webinar. We're very pleased to have Prentice Bisbal from the Princeton Plasma Physics Laboratory here to talk about how to build and package open source software. As a reminder, you can post questions either through the YouTube live chat or through the Slack channel. With that then, Prentice, welcome, and I'll turn it over to you.
Okay, thank you, Scott. As Scott said, I'm from the Princeton Plasma Physics Laboratory. I am a lead software engineer here, but don't let that title fool you. I'm primarily a system administrator, specializing in high-performance computing, and I've been in this role for approximately 20 years. And a good portion of my responsibility is managing the software that we have installed on our clusters for the users to use. And I think that is a great skill that a lot of computational science should have. So my goal for today is to share some of what I've learned over the years about how to install and manage computational software, open source software, for either your own environment at work in your home directory or on your personal laptop. And I'm also going to talk a little bit about some tips for packaging open source software. I have to admit the title is a bit of a misnomer, so I'm not going to go into detail about how to package open source software. I'm going to just give some advice, and I'm going to say bring up some pet peeves that I've come across as somebody who's been doing this for a while. So with that, let's get started. Let's see. So my motivation with this, like I already gave you my bio, and my motivation is, I have a BS degree in chemical engineering, and I think for most people who get a background in engineering and sciences, we probably had the same experience. I was taught an introductory programming class as a freshman. My sophomore year, I had to take a numerical methods class. And then I didn't use any of that again till, say, the last semester of my senior year. And then I was in a rush to tie it all together. And I imagine those of you who went to college a little earlier, you may not have even learned a lot of that stuff. Or if you're a graduate student or just out of college, you may have had a similar experience where you learn some very basic stuff and then you don't learn a lot of the other stuff you need to be effective in your position. And I'm hoping that this training today will help fill one of those gaps. As I said, I've been doing this for about 20 years. I've installed open source software, built these packages, gone through the process I'm going to share with you today, probably thousands of times. And I've always worked in a smaller environment where I don't just do the system administration, I'm also responsible for user support. So I have a lot of experience working with users and seeing where their issues are. And a lot of what I'm going to teach you today and try to emphasize has been based on that experience. One very key experience I had with that was in 2009 when I was working at another employer. We hosted a summer program in computational astrophysics. And the instructors asked me to set up a dedicated cluster for the students to use during the 2-week training course and install all the software on it that the users were going to use, all the computational astrophysics software that they were going to be learning how to use during the 2-week period. But the instructors didn't want the students to use that unless it was a last resort. They preferred that the students learn how to compile and install the software themselves so they could be self-sufficient and that they could do their homework on their laptop or wherever and take these skills back to their home institution and install the software there. Now, the instructors set up a mailing list so the students could help each other with their homework and discuss their homework issues and stuff like that. And interestingly enough, the entire mailing list was not about how to use the software once they got it installed or any of the concepts they were learning in the class. It was all about how do I get the software built and installed on my computer. And over that 2-week period, I spent almost my entire time via email, providing support to the students via email and helping them debug their issues. And I found that most of the issues were related to basically path issues, meaning that the preprocessor couldn't find the header files that the software needed, or I couldn't find the libraries that the software needed at the linking stage. And based on seeing hundreds of people have the same problem, I kind of broke it down and explained it. You know, if you see the problem here, if you get this error, the problem is here, and here's how you fix it. If the problem occurs here, this is how you fix it. And so that's hopefully I'm going to be able to provide the same support and instruction to you today. Now, if you're asking yourself, you know, as a computational scientist, why do I need to know how to build open source software? Here's a few reasons. One, computational software is a tool of the trade for computational scientists, right? Having the latest or best tools can help you be more productive and be more on the cutting edge. And I'd say those of you who work in the computational sciences field exclusively, you're kind of at an advantage over other scientific fields. Like, for example, a computational chemist might need a NMR spectrometer, and those are, you know, hundreds of thousands of dollars. They have to be they have strong magnetic fields, so they have to be built in you have to be put in a specific environment. So there might be some facility preparation to prepare a room to have them in there. You can't have like a lot of metal too close to the magnet because it will interfere with the magnetic field. And they have to be, you know, properly conditioned environments. They use a lot of liquid nitrogen and liquid helium to keep the magnet cool. So you got to have safety instrumentation in there to make sure that the environment is safe for people to continue to be in. And so if you're a computational chemist and you need an piece of equipment like that, it could cost hundreds of thousands of dollars and take possibly months to years to set up your environment to have it installed. With software, you know, you can download it, build it, and in a couple hours, you know, download all the packages you need in a couple hours, have all the tools you need to do your work. So I think in that way, you know, we're very fortunate, and knowing the skill can help you quickly get what you need to do your job. Now, some of you might be thinking, well, doesn't my Linux distribution come with everything I need? And the answer to that is no. Linux distributions are providing more and more of the basic libraries, but they often don't provide all the libraries. And on top of that, most of the Linux distributions, or the software that they include with them, are usually behind the leading edge. For something like Red Hat Enterprise Linux, which by design uses older versions of software to guarantee more stability, you could be several years, if you get the latest version of Red Hat Enterprise Linux or any of its derivatives like CentOS or Scientific Linux, you could be several years behind the leading version. And from my experience, I can tell you sometimes software will need newer versions than what comes with the operating system for those, like, you know, more fundamental libraries. So you'll end up having to build a lot of software yourself and installing it yourself anyway. For those of you who, you know, have an institution with an HPC or, you know, IT department that supports high performance computing, they may not have adequate staff to install the software you need in a timely manner. So you may put in a request for a piece of software you need right now, but it may be several days to several weeks or more before you can get it installed and be able to use it. On top of that, some institutions may have policies that they only install release candidates of software, you know, final release versions. So if you want a new feature that is not in the official release yet, you may want to, you know, you may have no choice but to download and install it yourself. On top of that, there seems to be a trend where I see a lot more computational scientists doing work on their laptop. A few years ago, you know, laptops weren't really powerful enough to do anything significant on them. But as processors have gotten more powerful and more energy efficient, I see a lot more of the researchers I support doing work on their own laptop, whether it's a company-owned one or their own personal laptop. But one of the issues with that is you generally can't get as good support on a laptop as you can on the cluster at work, right? Because you might be traveling and I can't log in your laptop while you're traveling and install the software you need, stuff like that. So this is a good skill to have. So if you're traveling and you're at a conference and you meet you're talking with some other collaborators and you guys decide to work on something, or somebody recommends a piece of software that you should try out, you could quickly download it and install it and get working yourself. Now, for those of you who package your own software, you know, why should you care about how well you package it? Well, you know, this is something that's only necessary for those of you who write code for others to use. But in the academic research world, there's the whole publish or perish mentality. But beyond that, there's also how often is your research cited, and particularly with software, I find that people look at that metric a lot. You can write a paper on research, and it gets published. People seem to be okay with just the fact that it gets published, and I know some people do look at how much it's cited. But say you're a researcher who is being funded to develop a piece of software. The funding agency might want to see how many people download that, because that's something that's a metric that's easy to do, right? You can look at your web server logs and see how many people have downloaded your code. And, so it becomes a virtuous circle like I've illustrated here. If you make your code easy to build, it's more likely to be installed. If it's more likely to be installed, then it's more likely to be used for research, and then it's more likely to be cited. And then you can, show how many times it's been used, or how many times it's been downloaded, or how many times it's been cited, and then you can get more funding. And with that more funding, you might be able to hire more developers or get better resources to help you make it better. And then your code just keeps getting better, and it becomes a virtuous cycle. I've worked in a few places where the researchers developed code, and I know that was always an issue, was trying to demonstrate that the code that they were developing was providing a benefit. When they were up for reapplying for a grant or extending funding, those kind of metrics would be something that they would try to bring up in their grant application. So in the late 90s, early 2000s, I used to read the Linux Journal a lot, and they used to, talk about the open source open source 5-step as an easy way to build software. And for the fictitious package foo version 1.2.3, it would look something like this. You use tar to unzip the tarball. You cd into the resulting directory. You type /configure, make install, and then everything is done. Well, I can assure you, while that will work on anything other than your own personal system, I would not do it that way. For one thing, you're not telling it where to install the software. And by default, it usually installs in user local. And that's generally not what you want. Or you don't want it to install at the top level of user local. You want to install it in a subdirectory there. And it also doesn't talk about how you would enable or disable different features. And it also doesn't tell you what to do if something goes wrong. And I can assure you, things will go wrong. So before we get too far into it, let me just give you a demonstration of what it looks like when you do an install. For this demonstration, I'm going to be using a simple program from GNU, the GNU Foundation, called Hello, which is a basic demonstration program that's really designed as an example of how they want their tool packaged, and how everything should work according to their standards, how the configure script should behave, software gets put in the right location, all that. So let me switch to a terminal window, and we'll just walk through that right now. So I downloaded the tarball from the website for this package. If you just do a Google search for GNU Hello, you'll come to the website. So I downloaded the tarball into var temp. Actually, let me start over. So I untarred the software, and I'm now in the hello-2.1 directory that was created when I untarred the software. Now, since that 5-step, I last read about it in Linux Journal years ago, the standard now is you don't build directly in the source directory. So you want to create a separate build directory where the build takes place. So I'd already built this because I did a dry run, and I created a directory within that directory called build. And let me do a make dist clean. So as you start this, the build directory will be completely empty because you just created it. And now the configure script is a step, is in the directory above. So I got to use 2 dots to indicate the directory above, and then run configure from there. Okay. Now when you run the configure script, there is a number of options that are available to you. And if you do -- help, you'll see them. These options are going to vary from package to package. So you should always look through this for every package you build and see what options are available for that particular package. So the first one I'm going to point out, variable that you should almost always set, is this prefix directory. So the prefix is basically the prefix is a directory where you're going to install the software. Like I said, it defaults to user local, but you don't want to do that, because if you do that, the libraries are going to go in user local lib, and then the header files are going to go in user local include, and then the binaries are going to go in user local bin, and so on and so forth. Now the problem with that is, as you install more and more packages yourself, you can't really keep track of what files belong to what package. So I prefer instead that you install it in a directory, each package and version in its own directory. And I have a slide on that. And for people who are going to be building software on a shared system, or actually even your own system, I recommend you install it in your home directory, unless you're really experienced with system administration. And I recommend you install it using a nomenclature, something like this. In your home directory, maybe you create a directory named apps, and then you have another directory called app name, and then app version. And by doing this, it allows you to keep multiple versions of software installed on the system at the same time. Now you will have to set up your environment, to find these different versions, and I'll get to that a little bit later. But overall, that makes package management a lot easier. When you have your distribution and everything is in, like, say, user bin, and user lib and user include, that's a lot. You have professionals who are spending all their day doing that, and when you do an update, you usually don't go back and have multiple versions of a package installed. So this, using a nomenclature like this, I find is a lot easier. And this is what I do here at work. We have a file system named user PPPL, and we install everything in there, but it's like user PPPL / app name / version. And then we use the modules environment to set up the environment so that somebody can use that. Now, I don't want to get into modules today because we don't have enough time to go through all that, but that's one way you could do that. Now, let's get back to the demo here. And so you have a, whoops, am I in the right window? Yes, okay, sorry. So you have the prefix directory, and then there's going to be other directories, other options for more fine-tuned control. I recommend you avoid them unless you know exactly what you're doing. And then if you scroll down, we'll start to see some different options. Now here, there's one I want to point out right here. This one, it says disable silent rules. I personally like to specify that option, because what happens is, if you don't, you enable silent rules, which then means the make process is not very verbose. And like I said, it's very common to run into issues, and often when you have this, you don't see the errors as much. So I always personally like to disable silent rules so that I can see everything that's going on. Is it a lot of useless input most of the time? Yes, but when you find a problem, it provides more useful information so you can see what the issue is.
Prentice,
Yes?
we have a question.
Okay.
The question is, what about make uninstall? Does that not uninstall what's been installed into user local?
I would have to see an example of it, but typically the make uninstall would only be in the build directory, right? So typically you don't keep your build directory around forever. So when I'm done installing software, I usually delete the build directory. For example, right now I'm building in /var/temp is where I unzip the software and I'm in there, which is by definition a temporary directory. And I usually don't keep the source code around. So once you're done with your build and you delete the source code, that make uninstall option probably would not be available. Now I'd have to see a specific case of that. but I generally have never relied on something like that for that reason. Now, on top of that, if you did install and use your local, you would not be able to have multiple versions of the same package around. And I personally like to have multiple packages around so that if the newest version has a bug, you can easily revert back to the earlier version without having to go through this whole build process again. And then once you move to the new version and you're 100% sure you don't need the old version, then you can delete it. As a sysadmin, I can say that's a struggle for me because there's always some user who wants to stick with an old tried and true version that's 20 years old and doesn't always want to give up. So, as a professional practice, I always try to keep at least several versions of a package around after I install the older versions, I should say, after I install a new version, for those users who either just refuse to use something new or they know that there's a bug in an older version and a newer version that affects them for some reason. So I hope that answers your question. So as you go through here, and again, what you see here is going to be different for every package. Now down here at the bottom, this is always last, there's going to be a bunch of influential environment variables that you can specify that will affect the build process. I will get to these a little bit later in more detail, but the most important ones are CC. This is the C compiler you're going to use. If this program used C++ code, you would have an environmental variable called CXX. And if it was Fortran, you might have an environmental variable called FC for Fortran compiler, F77 if it's Fortran 77, or F90 if it wants you to specify a Fortran 90 compiler. These days, since most Fortran compilers support all the different versions, you generally just specify FC. Now, C flags would be an environment variable where you'd specify flags for the C compiler. These might be optimization flags like -03 if you wanted to use optimization level 3, or if you wanted to do some other kind of optimizations or some other more specialized behavior of the compiler. LD would be the linker flag, and that would be specifying libraries, directories that you want to search for in a non-standard directory. And I'll get to that a little bit later. Libs would be specific libraries you want to pass. So first you would set the library directories you wanted to search, and then you tell it the exact libraries you wanted to look for. So if you want it to link against BLAS, you might specify -L BLAS there, or FFTW3, you would specify -L FFTW3 there. The CPP flags, this is for the C preprocessor. You would use this to specify additional directories to search for header files, like an include directory. And you do that with a -I and then the name of the path as it shows right here. And then CPP is the C preprocessor. Very rarely do you have to specify a different C preprocessor, but I did find that for one particular package, there was something about it that when I was trying to build it with the Portland Group compilers, it did not work with the Portland Group preprocessor. So I actually had to use that flag to tell the software, which was otherwise going to be built with all Portland Group compilers, to use the GNU C preprocessor. So this particular package, the hello package, is a very simple package. There's not a lot of options to it. It basically just prints hello world. So to configure that, so I would just do configure, and I'm going to specify a prefix. I'm going to put it in my home directory in apps, like I showed you, hello 2.10. And the environment variables, rather than defining them as proper environment variables, you can also specify them on the command line. And the preferred way of doing that is to make them an argument to the configure script. That way you don't have to export them and define them as a true environment variable. So just to show that, I'm going to specify GCC to make sure that it uses a GCC compiler. On this particular system, it's the only compiler I have, but in a HPC environment, it's not uncommon to have the Intel compilers, the Portland group compilers, GCC, and maybe LLVM and some other compilers. And I always recommend that you specify the compilers you want to use in an environment like that, because different packages will have different ideas of what a compiler should take priority. For example, in one package, if you have Intel and GCC, one package might prefer Intel over GCC. And so while you're used to other packages finding GCC first and using it, other ones will say, hey, there's the Intel compilers in my path, I'm going to use that one first. So if you have multiple compilers on your system, I would recommend at the very least specifying which compilers you want to use. Now, what I always like to do is I like to take notes, keep a log of what I'm doing. So for those of you who aren't familiar with this syntax, this is bash shell syntax, which says, take the file handle 2, which is standard error, and tie it to file handle 1, which is standard output. Now I'm going to put that into a pipe and pipe that into T, and then run config. And then put that in a file called configure.log. Now you don't want it to be config.log, because config.log is actually the name of the log file the configure script builds itself, which will hold different information. And by doing this, one, it keeps a log of everything all the output from the configure script, so that I can go back through it later if there's any errors. And it also allows, the T command will also send the standard output not just to the file, but to the screen, so I can see the progress in real time also. And we'll take a quick look at this when it's done and just see what it's doing. Basically what it's doing at this point is the configure script is probing the system to find what is available in your system. It's looking for if there are certain header files that come from certain packages. It's looking if certain libraries exist. It's looking if certain commands are in your path that it will use, for example, like the C compiler, stuff like that, so that it knows exactly what it needs to do to compile the code in your environment. And then when it's done, it creates make files. And then the make files are used by the make command to actually do the compiling process. And you can see here the last few steps are creating make file, and then related make files, and then it's saying creating make file down here. Now let's look at that log file real quickly that I created with the T command, and you'll see some of what it's doing. So you see it's searching for Gawk up here, right? So it's searching for the Gawk command because it needs that, which is the GNU awk command. So it's looking in your path for that. It's looking in your path for GCC, and then you'll see here it's actually trying to see whether the C compiler works. Now, typically how it does that is in your temp directory, it will create a very small C file and then try to compile it. And then it'll also check to see the output, and you'll see that here. And then it does a whole bunch of tests like that. I could be here all day going into the details about how these different things work. But just know that in the background, the configure script is testing if commands exist in your path, testing if it can execute them and gets and executes without an error. And it'll be trying to build small sample test programs and seeing if the output works as advertised. Now, in this output, you'll see a lot of no's also. Like, for example, you'll see it's finding certain header files and it's saying yes. That's okay. Now, you'll see a lot of no's also. That's not necessarily bad. That just means, okay, there's no minix config.h. Fine, I'll search for something else that provides the same functionality. So if you're compiling software and you see a lot of no's, that's not necessarily bad. That just means it's trying something that doesn't exist. It's looking for an alternative way of doing it. And depending on what libraries you have on your system, there could be more than one way to do things. For example, BLAS. There's multiple libraries out there that provide BLAS functionality. There's the BLAS libraries from Netlib. There's BLAS that comes with the Intel Math Kernel library, MKL. There's used to be the AMD Core Math library, ACML. There's OpenBLAS. So there's multiple BLAS libraries. So if you had something that was using BLAS, it might try to determine which one, if any, exists in your library, in your environment. So seeing no's like this is not necessarily an issue. If configure does come into an issue that's a deal breaker, it will stop and report an error, and you'll recognize that when you see that, because it's pretty obvious. So when you scroll through this or see it going on your screen, if you see yes or no at these different stages, it's not really anything to be concerned. So now the next step, now that we have it configured, you'll now look, if you see in the directory, there's a bunch of files, including a make file. And if you looked in these subdirectories, you would see more make files. There's like a cascade of them. I don't want to get into that, because now we're going to be talking about GNU make and make files, which is a whole topic unto itself. So the next step is that you would run make. And again, most of the issues, if you made it this far, some of the issues, even though you'd expect the configure script to catch all the issues, and in theory, if configure completes successfully, your program should run. That's not always going to happen. So again, I like to take all my output from the make command and tee it into a log file. And for big packages, this is important. For big packages, it could take 15 minutes, 20 minutes, maybe an hour to build the package. There are some packages, really large ones, that might take overnight. And if it's running for hours and you're running into issues, you don't want to run make again and then try to watch to see where the errors are. So keeping all this output in a log file will make debugging in the future very good. Now, very much quick, sorry, let me catch my thoughts here. Keeping these log files to your successfully built the software will make troubleshooting go by much quicker than if you have to do a make again. So we'll do the make, and you'll see it go through. And what you're seeing now are the actual commands run by make. For example, here's a GCC command right here. Here's another one here. And this one, it's actually, what's it doing here? It looks like it's linking to libhello.a, which is a static library. But most of this might seem like garbage unless you're a developer who builds software all the time. But trust me, when you see an error, it's very helpful to have this information. And usually when you see an error, it's on like a GCC command, like an actual compiler command. Like you see here, sometimes this is just moving one file to a different name. But this can be very helpful as you get more skilled at this to debug issues. So going back to that 5-step, if you remember in the 5-step, there was a... the next step would be make install. But generally, I like to run make check. Not every package provides this functionality. When you run make check, what it will do is it will run a bunch of simple little tests that will help you, that will check the functionality, basically like regression testing, and see if the program is behaving correctly. Again, this hello world program basically just says hello world. There's not much that it does. But if you're doing something that does a lot of math, like say, for example, FFTW or like BLAS routines, you want to make sure that it's getting the right answers, because you certainly don't want to be publishing research on incorrect numbers. Or in my case, one of my biggest fears is that I build the mathematical library and it has some kind of error that a make check would have found and I didn't find it. And then somebody's doing research, and then they either waste months of time because they got the wrong answers, or they published a paper which then had errors. Now, again, not every package has a make check, and sometimes they call it make test instead of make check, but make check is usually the standard convention. And again, I redirect the output to a file that I can keep track of. Oh, I forgot the T. So there you go. Again, this is a very simple program, so this went very quickly. On some other environments, especially with more mathematically oriented packages, this could run for longer than it takes to build the software actually, because it has to do, sometimes this can be very computationally intensive and it takes a long time. Now, in this particular case, we get very nice, easy to read and easy to understand output. You don't always get that, but in this case we did. So it's very clear that there's a total of 5 tests. It passed 4, and it skipped 1. Now, if you see an X fail, that basically means expected to fail. So that means that there's a test that the developers know would fail. Maybe it's something, a new feature they're working on that isn't quite ready yet, right? So if you see an X fail and it has a number, that's okay. If you see a failure, obviously that's something you should be concerned about. Or if you see something that says errors. I've never seen anything that actually produces an X pass, but I would imagine it's nothing to worry about. Now, unfortunately, sometimes these make checks aren't fully baked, and you'll see errors, and the errors are actually something you can ignore. What I generally recommend is you can't always tell that just by looking at the errors. If you do get errors, Google on the error messages you see in the output, or go to the mailing list or the website for the software. Sometimes in the documentation, they'll say, if you do a make check, you might get these errors. Other times, it might be brought up on the mailing list. Somebody does it, and then the developer will say, okay, yeah, you can ignore those. Those are only really for us. And we know that they break. And I hate when developers do that because, people like me try to rely on those tests. And when they do that, it makes it harder for us to put any faith in those things. But again, I always try to run them myself. Now, sometimes these make checks will be the output will be very, very long. So a quick check you can do to see if it passed it would you grep that sheet, it does the same thing. And if you ignore the case and grep for pass or fail on that file we just created, it will show you all the occurrences of pass or fail in there. And most of the time you will see it will report a pass or a fail when something fails. So this is a very quick, easy way of finding out whether your program passed or failed. Now for the final step is to do make install. And what this does is it copies the files to the final location. If you remember earlier, I specified a prefix to be in my home directory. What it will do is it'll copy those files from where they were built and put them in the specified location in a proper hierarchy, and we'll make sure that the permissions are correct. We're seeing errors here because I had already installed this earlier. And it looks like I might have done it as root, because usually it should be able to just delete it. So I did the test run of this earlier, so we can ignore those for now. If we go to that directory, sorry, I don't normally use my laptop, so I'm not used to this keyboard. So please pardon my typographical errors. So you see here we have a bin directory and we have a share directory. And the share directory is where we can ignore that for now. But basically, the share directory is where a lot of architecture-independent information goes, like data files, like these messages for internationalization, error messages. And then down here, we actually see the man page. And then in the bin directory, we actually have the hello, right? So if you go into bin, maybe that's a little easier for you to see. We have the hello program, which we can now run. And it shows hello world. And so we know that the program works. Now, we're not completely done now, because now we still have to set up our environment to support it. One thing we want to do is add this bin directory to our path. So here's our default. Here's what my path is to begin with. Oh, sorry, wrong thing. Now that's basically the default path, and what I would need to do is add the path to that executable to my path so I can actually use it without typing the full path to it every time. And I put the new path first because in general you want the new software to be found before the old version. For example, if I just installed the new version of GCC, and I put that path first, and I already have GCC on my computer, when I type GCC, it's going to search for the first one it finds in its path and use that. Whoops, wrong variable name. So now if I do which hello, we can see that it's the hello that's in my home directory. So we also want to add a man path. So we need to add that to our environment. You know, we need to add the man page directory. Oh, I made a typo. Sorry about that. Now, if I do man hello, it will show me the man page for the software I just created. Now, when you get done and everything is right and you test your software, you're going to want to add these to your, make these changes to your environment, to your .bash RC file, or whatever your shell is, to the proper RC file, so that when you log in, these are set. If you use modules and you're familiar with modules, basically modules make these changes for you when you load the module, and then undo those changes when you unload the module. But again, that's a whole different topic we don't have time for here. So I just went through a very basic example that was very simple and had no errors. But like I said, you'll often run into errors with this. And most of the errors are that the build process cannot find, the compilers cannot find paths that it needs. And some of these will look like this, these errors. Let me scroll through here. For example, if you can't find a header file, and that's using a source code, there'll be an include statement like this. In fact, this is the line that's showing the error. And first thing you want to do to debug this is make sure that the package exists on your system. If it's a package that you think is included with the operating system, like a basic C package, or something that you think is included with the operating system, if it's like Red Hat, there'll be a Debian package. The package you need will be the development package, which will have a -dev or -develop in the package name. If it's software you installed yourself, you then need to specify the location with the -i switch to the compiler. And let me see if I can provide some examples of that. I do have an example somewhere. I just can't remember where I put it right now. Okay, yeah. So in your GCC command, right, you would need to put this here, right? -i, which tells the compiler basically add this directory to the preprocessor include path, and then the path to your directory. In this example here, I'm using FFTW 3.3.8, which was another example I was thinking of going to. Now you can add this as much as you want. You can add as many -i switches as you want, and the preprocessor will look to them from left to right order. So we'll look at them in the order they're specified on the command line. But remember, where am I? Okay. So remember in the configure, if you looked at the oh, sorry, wrong name. On multi-user systems, I always put it in var temp p bisbal so people know who created the directory and who was working there. But I didn't do that in this case. So if you remember, at the bottom of the configure, you have these CPP flags. So if we needed to specify a path to hello, say we were linking another package against it and it provided an include directory, let me use my FFTW directory, since that's real, right? I built FFTW 3.3.8. So if I was going to compile something with it, my configure would look like this. I would add this to my configure. Wherever say it's called app version 1.2.3. Then I would specify the CPP flags here. CPP flags equals -I, and then the path to the include directory, which would be home, apps, FFT, TW 3.3.8, include. All right? So you do something like that. Now, another example would be of a compiling error is that it can't find a library. So for example, if I was using libffTW, that might say can't find -L FFTW3. So to fix an issue like that, one, again, always make sure that you have the software installed on your system. And on top of that, sometimes I've been finding lately packages distributions don't always install the static libraries. So sometimes if a package is trying to do a static linking, you got to make sure that the static libraries are installed too, not just the standard libraries, which would be shared libraries. So to fix that problem, we would have to add the LD flags, right? So we would have to do this. And again, the path to the install directory. And then we would have to provide the libs. We would have to define the libs variable also, which would be in using the FFTW example, just be L FFTW3. Now, and then it would build. Now, unfortunately, I wish I could do a real example with this with a bigger application, but unfortunately, building this software takes time, and I didn't want to waste all my time doing this presentation watching it build. And again, that's most of the issues I have found have been with path issues, not specifying it correctly. Now, for those of you who know how environment variables work, you could specify these as environment variables and have a much shorter command line. But I recommend that you do it this way instead. The reason being, when you're working in multiple terminal windows, you might set those environment variables in one terminal window and then have another one open and then run the actual configure command there or the subsequent build commands. And you'll run into errors and you'll be like, hey, I thought I just defined all this stuff. And you did, but in a different window, so it doesn't work. So if you do all this on the command line, it's a little bit easier to keep track of what you're doing step by step. Now, the other reason I like to do it is I keep detailed documentation in ASCII files and text files. And by doing this, I can cut and paste the entire command and know exactly how everything was set up and do it that way. Now, if you're not familiar with where files should be, I recommend familiarizing yourself with the Linux file system hierarchy. The Linux file system hierarchy is a standard that most Linux distros adhere to, and it defines where all the software should be installed on a Linux distro, and some standard best practices for local files. Like it does talk about putting stuff on user local and in /op, which are common locations for installing software locally. But look at this section in red. Local placement of files is a local issue, so FHS does not attempt to usurp system administrators. So what that means is even if you're an expert at the Linux file system hierarchy, that means for software that has been installed locally by your local system administrators, that all goes out the window. But I personally try to follow this as much as possible and install software in user local or in /op. And I try to advocate that other sysadmins follow the same practice so that a user could just learn the Linux file system hierarchy standard and know everything. Well, not know everything, but have a good idea of where things should go. So this is a diagram I created, the file system hierarchy standard. I don't recommend you try to do this yourself because it was quite tedious trying to draw all this, and I'm sure there are some things I left out. The directory names that you see in this like greenish blue, bluish green color, greenish blue color are optional. The ones that are in orange are things that are unique to the Linux operating system. And this can be overwhelming if you're new to Linux and want to try learning this, but for building software, you don't need to know all of it, right? I've simplified it to this. This is what you would need to know. You basically need to know where the bin directories are in case you need to add one to your path because there's a command missing and you want to add it. You want to know where the library directories are, which are these are the ones in root. It's either the top level. You will have opt, bin, and include directories, possibly under opt. If you have software installed in opt, if you have stuff installed in user local, you again would have bin, include directories, lib directories, library directories, and sbin, which is sbin is just like bin, but it's for system administration commands that you don't always need as a regular user. So they're put in a separate directory. Now, if I wasn't clear about this before, the include directories are where the header files are kept for software that the preprocessor needs. And if you know this and you're familiar with this aspect of the file system hierarchy, you can usually figure out where the files are and search for them and then add them to your flag so that the configure script can find them correctly. So these are kind of the takeaways from this part of talking about the file system hierarchy standard. Now, even though they're standards, I can't emphasize this enough. There might be site-specific locations in your environment that you need to check. For example, if I go back to this slide, I typically install software in user PPPL. That's our custom here at the Plasma Physics Lab. And I've seen other places use a similar convention. That's not explicitly stated in the file system hierarchy standard, but the file system hierarchy standard explicitly says we allow that sort of thing. So I have a bunch of stuff here, but after I was going through my slides, I realized I wasn't going to be able to present it that way, which is why I haven't really used my slides that much. So at this point, I just want to close and go over some resources. Oh yeah, one other thing I want to go over. If you screw up when you're building, like for example, say you keep running into issues and you get to a point where you want to start over as if you're starting from a clean slate. You don't need to completely delete all the software, the entire software directory, source directory, and start over. Where you did the configure in the make file, there's usually a command called make clean. And so say you built it and you realize you had the wrong flags, you can do a make clean and it will remove all the object files it created. Some packages will also have a make dist clean, which will be even more thorough. That will even remove like configuration caches and stuff like that, so that you're starting at a clean slate without having to completely rebuild everything. So I wanted to keep this to an hour. We're almost getting to an hour, so I just want to go through a few other things. Here's some tips. Like I said, I typically always specify a prefix so that I can keep my different versions of the software separate and have multiple versions installed at the same time. And then by changing my path and other environment variables, switch between the versions. And again, if you're familiar with modules makes that much easier to do. As I showed, I like to disable the specify this when it's available, because what that does is it makes more verbose output, which makes debugging issues easier. I like to build both shared and static libraries. So I like to enable both of these features. Typically these days, a lot of packages will enable shared by default and not enable static, but that's not always true. FFTW3, for example, prefers static, and then as a default, and enabled is optional. For me as a system admin in particular, I like to specify both because some users prefer static, some prefer shared, and I like to make sure everything's available for my user. And generally, I find that you never know what situation you're going to be in the future. I've been in a few situations where some packages will not build against dynamically linked libraries that require static. for one reason or another. So just to make sure I don't have to go back and rebuild the package that I built a year ago, I just like to cover my bases and do all that. Let's see, we'll skip that slide. So in closing, for building software, here's some resources here. This is the definition of the file system hierarchy standard, which I highly recommend if you're new to Linux or not, you don't feel you have a strong foundation in it. I recommend you take the time and read through this. You don't have to know it line for line, but I look at this as like the map to Linux. So if you're having trouble finding your feet in Linux, I think this might be a good thing to read. It's not very wordy. Some of it might be dry and technical, but it's, like I said, it's not a lot of reading to do. It's worth learning. And you can go to that website and find it there. If you're new to building software and using compilers in general, I highly recommend this book. This used to be available completely online for free. The company Network Theory, which was in the UK, which Brian Goff, I think is how you pronounce it, or Go, I think it's Goff. They apparently went out of business in November of last year. So you can't find the official version there anymore. But there was a print version. There is a print version that's available on Amazon for, I think it's about $10. And if you follow this link now, it now redirects to Amazon. And I think it's worth the $10 since the whole content was online and it was kind of an open source book. There are some PDFs available online if you search hard enough that you might be able to find one. And in the GNU coding standards, section 7.1, they actually have like about a page description of how configure should work. And I highly recommend you take a look at that because it kind of basically highlights and summarizes everything I went over this morning. Now, I do want to speak a little bit about packaging software. And this is kind of a pet peeve of mine. And those of you who write software, please don't take anything I'm about to say personally. But I've built, like I said, I've been doing this for a long time. I probably built thousands of packages. I find the more scientific specific applications on average are typically much harder to build than your standard open source software. And again, that makes it harder for people to use your software. So if part of your mission of your grant, if you're grant funded, is to make people provide software that other people can use, I think it's very beneficial to you in your project if you put some time into it to make it easy for people to build and install your software. Some of the common complaints that I have is poor or no installation documentation. I've seen some very complicated scientific packages that have tons of documentation about the science behind their software and the algorithm it implements and fully defining the API and how every single function works, but not a single thing on how to build and install it. And I can often spend hours or days trying to figure it out on my own. No configuration process. The configuration process we went through here is using a configure script that is provided by GNU AutoConf. AutoConf is a tool that the developers use to create this script. So not every package has it. It doesn't automatically appear there. The developers have to consciously decide to create that script and put it in the package as a benefit for the end users. I've seen a lot of scientific libraries don't have anything like that. They say, here's a makefile, edit it to suit your local needs and install that. And often there's a lot of details missing about how to massage the makefiles to make it work properly. In some cases, I've actually seen that there's no make install, and I have to install the software myself. I've also seen where all the file types, whether it's the headers that should be in an include directory, the libraries that should be in separate lib directories, the binaries and data that might be somewhere underneath a shared directory, all in a single directory. No version information, and sometimes very indecipherable file names. Now, I know I don't want to sound like a complainer, but these things make my job easier, and to make everybody who you want to reach with your software makes it easier for you to reach them and take advantage of your software. So some suggestions, provide consistent version information in your software. There's this document, if you go to this website, semver.org, it's basically a standard for semantic versioning, and it explains what semantic versioning is there and how and when you should increment your different version numbers. For example, like when do you issue a uptick your bug fix version? When do you increase a minor version number? When do you increase a major version number? Stuff along those lines. And I would love it if every program included a way to check the version's information after it's installed. Sometimes that version information is only included in README files or the install documentation, or it might be included as a constant in a header file that may not be kept around after you install the software. It would be great if there was some way that someone could just run a command, or an existing command, you add a -- version switch that will show you that. Perfect example of that is GCC, right? If you do GCC -- version, it will show you the version information. A lot of programs have some kind of functionality like that. Sometimes when you download software, when you make your software available for download, the tarballs, as those files are called, don't always have a meaningful file name with version information in it. I believe it's on GitHub. If you check out them, you can create a tarball from a branch, and a lot of people just check out the master and just leave it as master.tar.gz, and that's not really a good file name, because if everybody did that, when I download the software, I'd have to create a different directory for every single package, which I do because I think it's a good practice, but I would have a bunch of master.tar.gz files in different places on a hard drive somewhere, and in 6 months or a year after I download them, would not know where they should be. Would not know what package they are or what should be inside them. Again, for developers, this is also important that your software adheres to the Linux file system hierarchy standard, which would mean that it uses like temp or var temp when it needs to create temp files. And then if it logs, it should log to somewhere in var log. Varlib and varrun have very special purposes, and that for users should be able to create dot files in their home directory that you could store preferences in, stuff of that nature. I'm actually dealing with a commercial software package now where I have an issue with that, where they want to create licensed temp files used by the license software licensing mechanism that writes in /user/ wherever the software is installed. Now that's a problem because /user is supposed to be read-only by everyone but root. And this software runs, when it's running as a local user, therefore it's trying to create files as a local user, as that user, in the user in underneath the user file system hierarchy. And that shouldn't be done. That's just bad practice. And so the recommendation is that I make that one particular directory world writable and readable, which again violates all standard practices for managing software. And so that software should have been written that those temp files get created in temp or var temp. For this type of file, they really should have been in temp rather than var temp. I don't want to go into the difference between those two. It's a little esoteric at this point, and that's in the file system hierarchy standard. I can't emphasize this enough. You don't need to just have effective documentation on how to use your software. You should have effective documentation on how to install it also. And you should try to follow existing standard and conventions for how you organize your software. And that could be some things as simple as the file naming and the directory structure, and even standards about how many tabs you use or spaces, and whether you actually use spaces for tabs or vice versa. I don't care what you use, because as you're building software, we don't normally see the code, but just be consistent with it. Like I said earlier, it's really great if you use some kind of installation and automation tool, like using GNU AutoConf, which the demonstration today was using the configure script created by GNU AutoConf There are other tools out there. CMake and SCons are two I've encountered somewhat, commonly, but they're not nearly as possible as GNU AutoConf. The configure script used by GNU AutoConf seems to be about 90%, 95% of the market. So if I was starting a new project now, I would probably look at that first and take a very serious look at it just because of market share over anything else. It's basically the de facto standard. The people at Kitware that make CMake probably would disagree with me, but I'm just telling it as I see it. But whichever one you use, just pick something and also document it. Even though GNU AutoConf's configure script is very common, the first time you see it, it's just as alien as anything else. So whether using GNU AutoConf, CMake, or SCons in your documentation, you should provide some kind of examples of how to use it to actually configure and build your software. And I think that basically concludes it. I do have some resources for packaging software here for those of you who are interested in doing that. Again, I'm not a software developer myself, so I'm not an expert on any of these. I just say you might want to look at these when you're starting a software project, and try to follow some of these standards here. This is a video I saw a couple weeks ago. This is by Kenneth Host. I don't know if it's Host or Hosty. I don't know how you pronounce his name, but he's the developer of EasyBuild, and so his job is trying to make hundreds of packages build automatically, and he gives a rather informative and entertaining perspective on it in this talk that's about 18 minutes long on YouTube. It's very tongue-in-cheek and very sarcastic, so remember that when you go into it. If you're a developer, it might, you might find some of it somewhat insulting because he's speaking at it totally from a package manager's point of view, but I think it's worth hearing and thinking about the issues he brings up when you start or trying to modernize a software project you're working on yourself. This is the first time I've given this talk in a format like this. Typically, I've given it to coworkers in a much more informal environment, and I would certainly appreciate any feedback you can give me on how to make this better. There was a lot more I'd like to go into, but due to the time constraints, it's really hard to fit that kind of stuff in only a 1 hour talk. And I would appreciate any feedback you can give me on this. I think in future talks, I'm just going to focus on the building the software and completely jettison the building the software part because I think that's enough to cover. And I'm not an expert on building software myself, so I think maybe I shouldn't be the one talking about it till I develop more expertise on it. And any feedback you guys can have that could make this a better talk in the future, I'd greatly appreciate it. Now that I'm done, if there's any questions, please fire away.
Thank you, Prentice. As a reminder, if you have questions, feel free to post them on the YouTube live chat or in the Slack channel. A question I would have for you, Prentice, you gave some good resources and you gave your own email for people to contact. Are there discussion groups that you would recommend people go to bounce ideas off people?
Yeah, not in general, but one thing I would highly recommend is when you're building a software package, if you run into an error, one of the first things you should do is, put that error message into the search engine of your choice, whether it's Google, Bing, DuckDuckGo, and see if you can find hits on it. Because unless you're compiling a brand new package and you're the first person to download it and install it, the odds are very good that someone else has already encountered that issue and has posted it to a mailing list or discussion group somewhere. And so you could probably save yourself a lot of time by doing that. That should always be your first thing. I would say if you find something on Stack Exchange, a solution, be careful of the answers. Now, if you're a beginner, you probably won't know enough to be careful. But as a more experienced system admin, I've seen people suggesting solutions that are really not best practices and could lead to further problems down the road. And I know that because I may have seen those problems myself over my years of experience. But I understand, younger members in my audience who are just graduate students or maybe even undergrads who are new in this field, maybe not having enough experience to see that. But, just try to take a somewhat skeptical eye when you're looking at solutions offered online like that. I highly would recommend for a package, if you run into issues, most open source packages have their own mailing lists. And if you can't find an answer via Google search, the next thing I would do is join that mailing list and post your error there and give them information like your whole configure command so they can see what's going on. And more than likely, you'll get an answer relatively quickly. I've never ceased to be amazed at the responses I get from the open source community with problems like that. And most of these mailing lists, for a project, the developers themselves are on the mailing list. And so, you can often get a response, it might take a day or two, but sometimes I've gotten responses as quick as minutes from the developer of the software himself. And sometimes they'll be like, oh yeah, this problem is because of on that version of CentOS or that version of Debian or Ubuntu, there's this issue. Or they might say, hey, thanks for testing. I didn't realize that was an issue. Give me a couple minutes or a couple hours and I'll have a fix for you. So I can't specify any general purpose mailing list, but I can certainly say if you're building a package and you run into issues, if that particular package has a mailing list for users, I would post to it. Now, some mailing lists, like I said, a mailing list for users. Some mailing lists have a separate mailing list for developers. You don't want to post on that mailing list if you're just a user. Those developer mailing lists are for the developers who are getting down to the nuts and bolts and getting into the guts of the software where they can discuss implementing issues. I would try to, if there's more than one mailing list, look for a project, look for the user mailing list. Smaller projects only have a single mailing list, but bigger projects will have multiple mailing lists, one just for announcements, one for users, and one for the developers. You want to post to the right list to get the best response.
Okay, we do have a question.
Okay.
More and more scientific software packages are deployed as containers, for example, Docker, that bring all dependencies along, sort of a lightweight virtual box image. Would a user still need knowledge about building and installing software as presented here?
I would say yes. I'm going to be honest. I am a bit skeptical of using container systems like Docker and Singularity to fix every problem. Sure, they do provide ease of packaging for the developer and for the user in some situations, but I don't feel they're being used adequately in a lot of cases. And it can be wasteful. For example, FFTW3, which I used in some of my earlier examples, it's a relatively small package, only a few megabytes. Are you going to download a whole system image just to use FFTW3? No. And the other problem is, say you're using, you need FFTW3 and some other scientific library. If they were each in separate Docker containers, I don't know if you could link between them and make that work. I really don't know much about the nuts and bolts of using Docker. For big environments, like if you wanted a complete environment that had all these libraries in them, yeah, I would see using Docker or some other container mechanism might be an easy way of doing that. But for distributing individual libraries like that, I don't think that's a good way to go. But yeah, if you want to provide somebody with an entire development environment, that might be doable as a Docker instance. But I don't see how it would be appropriate to install individual libraries just by putting them each in their own container. I also don't think it would function properly.
Thank you, Prentice. I actually had a question as well. So a lot of packages depend on each other, and frequently what happens is that one package can be built with two different sets of options or like optimization flags, and one user needs one option, the other user needs the other set of options, and and the question is, how do you handle such cases? Because you cannot build all packages with all possible options, like different like combinations of options or optimization flags. But still,
Yep.
you have to help users. How do you
Yes. Yeah, and
handle that?
uh, there's no perfect solution to that. I'll be honest. What I try to do is I try to build for the common case, for example. Um, like I generally try to usually when you build a package, the defaults are usually going to satisfy a large number of your users. One example I did show in my presentation was that I always try to make sure that both static and shared libraries are built, because some users want static, some people want shared. As far as like going into the more finer granularity, that's a very difficult thing to do. One package that this is a problem with is Petsy. If any of you have ever tried to build Petsy, there's like a million different features or options, like sub packages that it will build, and trying to make everybody happy in a situation like that would be very difficult. And my answer to you would be, don't try to make everybody happy. You might want to institute a policy or have a policy written about what you will and won't build for users. Now, what I think of doing for Petsy, because I do have multiple users who want to use it, is maybe do a survey. Just do like a Google form survey, or use SurveyMonkey and survey my users and say, what Petsy packages do you know you're going to components do you know you're going to use or you might want to use, and use that as your basis. One of the reasons I'm teaching this and want to make this something that a lot of computational scientists know is that there may be no happy medium. There are some packages where if you enable one feature, it disables another feature. And in that case, if a user requires something unique to them, I would insist that they install it themselves in their home directory or a project directory, a shared project directory if a whole project uses it, and sit down and teach them how to do this. I personally like to do as much for the users as I can, and I always recommend that the users ask me to install it for them before they go ahead and do it themselves. But that's not always feasible. Like I said, on laptops, we're limited as to how much support we can give somebody on a laptop. It's usually not at work where we can reach it and SSH into it. If it's somebody's personal laptop, that's a whole different story where we should have, I personally don't think I should have permission to somebody's personal laptop at the root level, stuff of that nature. And here I can say, where I work, the people that are using Petsy, most of them are pretty proficient at this. And so they understand that it's going to be difficult for me to make a version of Petsy that satisfies everybody's needs. So they build it themselves. They'll ask me for other libraries, but they'll say, my package needs Petsy, but don't worry about it. My package has a lot of unique requirements for the Petsy packages that get built and installed. So I'm going to take care of Petsy myself. So yeah, I think that's not an easy one to do. Set some standards. Like I said, I personally don't install anything that's not generally a final release version. I'm not going to install a release candidate or an alpha version, and I'm also not going to do a checkout from a Git repo and build that because when you do that, you're usually getting code that's still under development and it's not guaranteed to be tested and relatively bug-free. I'm sorry if I didn't answer your question, but I hope that gives you some clarity. One thing I can say that we do here is that, and I've seen other places do this, is like HDF5. You might want to build HDF5 with parallel support and without parallel support, and affix parallel or serial to the version name, and install them in different directories. Because if I remember correctly, there's certain features that you can't install if it's installed as shared libraries, or vice versa. I forget the details of that, but that's one way you can do it, is put a suffix on the version, when you install it, so that people can see that there's different options. But again, it's very difficult to manage a bunch of different options for every single user.
I would recommend to the audience that they consider tracking what's happening with the Better Scientific Software group that's formed at bssw.io. It's a collective that's growing to provide resources, information, and a place to learn more about developing good quality scientific software. In addition, in about the March timeframe, Computing in Science and Engineering will have a special issue on a topic called Accelerating Scientific Discovery with Reusable Software. And that's going to address some of the challenges that Prentice and others have covered about what makes for good quality software, and particularly focusing on the whole set of issues of reproducibility of scientific results too. And then we have one more comment from a participant saying, thanks, the nice thing about containers is they allow you to save and archive the software, the data, results extracted, and always go back to that snapshot for future reference. The key word here is reproducibility, which is paramount in science.
Yep. I just want to, Scott, I want to thank you for bringing up BSSW. I was actually going to mention them myself and forgot, but I have watched some of their webinars myself, and I think it's a great site. And the comment about reproducibility in containers is 100% true. That is one of the great things about containers. Like I said earlier, I'm always installing new software and trying to get users off of old software. But certainly if somebody did results 10 years ago and they get challenged to reproduce them, it would be great if I could easily give them the exact environment they had earlier. So I don't want to say containers are bad altogether. I just think that there's a time and a place for everything. And I think some people try to use containers for solving too many different problems. But taking a snapshot of an environment and making sure that that environment is always available in the future is definitely a perfect example of where containers are fantastic.
Okay, with that, there are no more questions, so please join me in thanking Prentice for his fantastic presentation today. And I just want to alert the community to the next set of upcoming webinars. Next up, February 13th, a webinar on 3D scientific visualization with Blender. And then on March 20th, a webinar on reproducible data analysis with SnakeMake. As always, we welcome your comments and suggestions for further topics, and we look forward to seeing you at a future webinar. With that, we'll conclude today, and thank you for joining us.